Okay, I think we can start now, guys. So good afternoon, everybody. So before I forget tomorrow, okay, what we don't have lab because we're gonna start the labs after I finish chapter 1. Okay. However, I want to give a lecture tomorrow. I'm not gonna take the 3 hours, okay, but starting from 4:30, right? So yeah, so I'm gonna give like 1 hour and a half or 2 hours at most, okay, tomorrow. Okay. So we're gonna meet here. Yeah, we're gonna meet here. I'm gonna during the lab session, I'm gonna give you a lecture. Okay. I think the labs are gonna start from next week. Okay. So before also I want to tell you, as I told you last time, guys, here I post all the lectures here. So the last lecture I recorded it and I posted it here. Okay, just in case if you missed anything in the lecture, you can go to the lecture and you can correct it or you can see it again. Okay, so last time. For sure, last time, number one, I told you in this course, we need the binary system, and I told you why, okay? As you will see in this course, computers can only understand or can only work on binary numbers. That's what you will see. Instruction, data, everything inside, multiplication, everything is gonna done in binary, okay? I told also, I explained why you need hexadecimal, okay? I made it clear, don't be confused when I tell you this memory location is storing the hexadecimal number 3A. That doesn't mean it is storing this number in hexadecimal, right? I'm just telling this way because it's more convenient for us to use it shorter, right? As I explained last time, okay? But you should understand it is stored in binary, okay? Also, for sure, we need to use decimal system because this is for us, only for humans, okay? That is why, as you will see later in this course, if you take a number from the user, from human, you are going to take this number in decimal, okay? But to send this number to the microcontroller, you have to convert it to binary, right? And we're going to do the opposite. If the microcontroller gives you a result and you want to display this result, you have to convert it to decimal, right? It's like translator, you have to translate. Okay? So you should understand how can you convert between the different systems, okay? I explained that also last time. Also, you should understand the prefix, the use of why you need to use a prefix like 0x, 0b, and other compilers may use different symbols, okay? Which is okay, but you need to use a symbol because this number can be binary, it can be decimal. You have to tell me, right? It's not something I can guess, right? So anyway, so here, for example, I made a mistake. I put a dollar. I think I corrected it on the version online because the old compiler we used to use $sign for hexadecimal. Is that okay? So I corrected it anyway. Also, you should understand what I mean by byte, half a word, double word, and so on. You should understand what I mean by least significant bit, most significant bit, least significant byte, most significant byte, and so on. Any questions? Is that what I explained last time? Okay. Also, last time I explained numbers can be signed or unsigned. Okay. Number one, I know this little bit confuses still. Who should decide if this number is signed? It's you as a programmer. The programmer should decide. So in the very beginning, I need a variable to measure something. Okay. So what you are going to measure is that signed or unsigned. Okay. And then you can decide, are you going to use signed or unsigned numbers? Okay. So, and also, I explained here. So for example, I also told you for n-bit, if you have n-bit number, okay? So if you have n-bit number, so this n-bit number can have in total 2 to the power n numbers, okay? So starting from 0, 0, 0, 0, this is the first number. You have here n bits, okay? All the way until 1, 1, 1, 1, 1, 1, 1, n bits as well. So how many numbers you have in total? You have 2 to the power n. Is that okay? Great. So this is true if the number signed or unsigned, it doesn't matter. doesn't matter. Okay, this is the whole space. These are all the different combination. What was going to happen is that, so this combination, if in case of unsigned numbers, I'm going to use all these combinations for positive numbers. You got what I'm saying? But in case of signed numbers, so I'm going to use almost half for in the positive side and the other half in the negative side. Is that okay? Also, I made it clear if your number is unsigned, so that means you can represent numbers from 0 until 2 to the power n minus 1. Okay, so this one is equivalent to 0, 0, 0, 0, and this one is equivalent to 1, 1, 1, 1. Okay, and in case of signed numbers, if your numbers are signed, so the range of numbers you can have, okay, it's negative 2 to the power n minus 1. Okay, the minus 1 is here. Okay, so 2 positive 2 to n minus 1 minus 1. So this one can tell you always the negative number is greater than the positive number by 1. Okay, for example, if you have 8 bits, so this one will be from negative 128 until positive 127. This is the range of number you can represent in 8 bits. Okay, guys? Okay. So, and also you have I'm explaining it here. Yeah. This is the range of numbers. In case of unsigned number, I give you the whole range. In case of 8 bits, 16 bits, 32, and so on. Okay. And this is in case of signed numbers. Okay. This is the range of numbers you can have. Okay. Also, I told you, now the question is that in case of signed numbers, numbers can be positive or negative. Is that okay? So how can we represent the negative number? You know, in the decimal system, we put plus or minus, okay? But here there is no plus or minus. So how can we represent negative numbers in case of signed numbers, okay? I told you there are different ways, there are different systems, but the system that most of the modern processors are using is called the 2's complement, okay? And as I explained last time, the idea of the 2's complement is for example, if you have this number here, this number 3, 1, 1, 0, assuming this number is 5 bits, only 5 bits, okay? Again, be careful here. When I give you example on 5 bits, you can use the same example in case of 20 bits, 30 bits, what I'm saying? So whatever the number of bits, I just give you example for 5 bits here. So this is number 3. If you want to calculate the 2's complement of 3, I told you, number 1, you have to calculate the 1's complement. 1's complement. And I told you the 1's complement, just flip the bits. This is the 1's complement. And then you have to add 1. After you add 1, so what you are going to get here, negative 3. So this is 3. After I calculate the 2's complement, I'm going to get negative 3. Okay. Also, if you calculate the 2's complement of negative 3, you are going to get positive 3. So the 2's complement, it's like you multiply the number by negative 1. You multiply by negative 1. Is that okay? So if I have negative 10, you calculate the 2's complement, you are going to get positive 10. You have positive 10, you are going to get negative 10. And so that's why in the quiz, okay? So we're going to have a quiz, but not tomorrow in the first lab. So in the quiz, I'm going to give you, for example, I'm going to give you, can you convert the 7? Give me the binary number, for example, for negative 7. Okay. There are different ways. You can calculate it in the, maybe there are different ways to do it. But in my opinion, the easy way, as I did here in this example, just to get number 7 first, positive 7, and then calculate the 2's complement. That's it. Okay. So negative 7 is actually 1, 1, 1. Okay. I'm assuming I'm using, like, for example, 8 bits. 8 bits. So because it's 8 bits, so I'm going to put here 0 and then 0, 0, 0, 0 because it's 8 bits. Okay. So, and then this is positive 7. So after that, I'm going to calculate the 2's complement of it. First is the 1's complement, and then you add 1. That's it. So I think I'm missing 1 here. So it's going to be 1, 0, 0, 0. I'm sorry, 1, and then 1, 1, 1. Okay. One more thing I told you last time, guys. If I give you a number and I tell you this number signed number, how can you know if this number is positive or negative? Pretty easy. All what you have to do, you have to look at the most significant bit. Okay, so if the most significant bit, for example, here, yeah. So here, this is 0. I'm assuming here we have, this is 5-bit system. So 5-bit system, okay? So this is 0 and 1, 2, 3. So this until here, all of these are the positive numbers. If you look at the positive numbers here, you can see always the most significant bit is 0. The most significant bit is always 0. Okay, guys? For negative numbers, so here, as you see here, okay, so always most significant bit is 1. Okay, so and also I told you, for example, if you have a positive number like this one, and I ask you to convert to decimal, how can you convert to decimal? This is what you have done before: 2 to the power 0, 2 to the power 1, 2 to the power 2, and so on. Okay, so in this example, the weight of this bit is 1, and the weight of this bit is 4. So this number 1 plus 4 is 5. Is that okay? But if I give you a number like this one, and I ask you convert this number to decimal, how can you do that? There are different ways, but the easy way, in my opinion, is you can, for this number here, this is -5. For sure, I'm not going to tell you this -5. I'm going to give you this number, okay? I'm going to tell you convert this number to decimal, okay? The easy way, calculate the 2's complement. If I calculate the 2's complement of this one, I'm going to get this one, +5, and then convert to +5. You get what I'm saying? So I'm going to get the positive version of this number. I can convert it easily, and then you have to put minus for sure. Okay. Again, maybe there are other ways, but this is the easy way to do. Another very important, and I know it's confusing to students, but please try to understand what I'm saying. It's confusing. Okay. Someone can ask me, okay, tell me when you give me, because I told you last time, for example, if you have here 1, 1, 1, 1, 1, 1, 1, 1, okay? This one can be 255, if this number is unsigned. This one can be -1 if this number is signed. Is that okay? So tell me how I can know, if you give me this number, how I can know if this is signed or unsigned. Is there any bits here I can check these bits to know if it's signed or unsigned? The answer is no. Okay, the answer is no. The idea of signed or signed, this is not something you can get from the bits. This is something you, as a programmer, you have to do it in your program. Okay, you will understand better later. You will understand it better later. But for now, I'm going to give you 2 examples to help you to understand it. Okay. So, as I told you, if you have this number, I want to display this number to the human. I have to convert the binary to decimal, right? Because a human can only understand decimal. In this case, we're going to have two programs, two subroutines. One subroutine to convert the binary to unsigned, using binary to decimal, using for unsigned numbers. We're going to have another subroutine, okay, for signed numbers, okay? And then in your program, if the processor gives you 111, 111, okay, that's what I got from the processor. And you know, from the very beginning, you decided this variable is signed or unsigned. So what you have to do as a program, a new program, you have to use the correct subroutine. You have the 2 subroutines. Is that okay? So if I input this one to this one, so the result is going to be 255. But if I input to this one to the signed subroutine, this one is going to give me -1. Okay, guys? Also in this course, as you will see later, I'm going to teach instructions for signed, instruction for unsigned. And you, when you write your program, you have to select the correct instruction, okay? For multiple, sometimes it doesn't matter, okay? For example, if you copy byte to byte, it doesn't matter if signed or unsigned, right? But sometimes it matters. For example, if I want to do something like that, if A is greater than B, For example, if I want to do something like that in assembly, A is 1, 1, 1, 1, 1, 1, 1, 1. Okay. B is 0, 0, 0, 0, 0, 0, 0, 0. Okay. Now it matters. Why? Because if this one is 250, if it is unsigned, 255, so yes, 255 is greater than 0. That's true. Okay. However, if this number is unsigned, so this one is actually -1, which is not greater than 0. You got what I'm saying? So if you want to do this comparison, that's why when I teach how can you do something like that in assembly, I'm going to give you two instructions, one for signed and one for unsigned. And when you write your program, you have to use the correct one. Maybe I spent too much time on this one because I know it's a little bit confusing to students. You understand what I'm saying? So the interpretation of signed or unsigned is should be considered in your code, not okay. You cannot get it from the bits. Any questions? Okay. Yeah, sure.
So like, what about when we enter the industry, we're called in and we have to analyze a currently made system, and let's say there's a part of like 20 bits. How do you know whether that's going to be 5 different unsigned ones or 4 different signed ones based off of like analyzing someone else's program when they call it? Is there a way to...
Okay, that's a good question. So you are telling me you don't know how the program is written. You don't know. So you don't know how if this is signed or unsigned. Okay, in this case you have to guess, right? But otherwise, for example, if you measure the temperature and you can see the temperature, for example, is -1. Okay, or you can guess if this is something like for temperature, and I know that temperature can be positive or negative. You can guess. There is nothing else you can do other than you guess, right? Or if you have the code, if you have the assembly code for it, you can see what instructions they are used with this number. If they are using signed, so it should be signed. Unsigned should be unsigned. Is that okay? I think here, this is very easy slide. I don't want to spend much time on this one. This is how can you convert decimal to binary. You understand how it works. For example, if here I want to convert it 52, you divide it by 2. When you divide it by 2, the result is 26, but the remainder is 0. Okay, and then you divide again 26 by 2. The result is 13, and remainder is 0, and so on. You can keep doing it this way until you get the result of 0. That's how we do conversion, and that's what you have done before. And then you can write it in decimal this way. Okay. Yeah. So before we leave this one, maybe I want to show you this one here. If you see here, guys, this is I'm assuming here we have 3-bit system, and here these numbers here are I'm assuming here the inner numbers here. I'm assuming these numbers are unsigned, and for the outer ones here, I'm assuming it is signed. So let's see, for example, the numbers from here until here in the positive side. So here from 0 and the positive side. If you see here, if it is signed or unsigned, it's the same number. So 0, 0, 1, 1, 2, 2, 3, 3. You got what I'm saying? So if the number is positive, so either signed or unsigned, it's going to be the same number. Okay. They are going to be different. They are going to be different in the negative part. Okay. So if you look at the negative part here, so just by accident, it was 4 and the -4, just by accident. Okay, but for this one here is going to be 5, and this is -3, 6, -2, 7, and the -1. You got what I'm saying? So in the positive side, they are the same, but in the negative side, they are different. Okay. Anyway, any questions? Okay. So the last thing here in this section, I'm explaining about data representation, how we are going to represent data. Okay. The last part here, I wanna talk about ASCII code. I'm not sure, maybe you should have heard about the ASCII code. Okay. So what is the ASCII code and why you need it? Very simple. So the idea is that, guys, we agree computers can only understand binary numbers. Okay. So hardware, and you already took digital system course, okay? Because everything has to be executed by the hardware. The hardware can only work on binary numbers. Is that okay? So, but for us as humans, we are using letters, right? We are using characters and letters, okay? So how can we, and hardware cannot understand these characters or letters, okay? So how can we solve this? very simple. You have to convert letters to numbers, okay? And that's what we call here ASCII code. For example, here, as you see in the ASCII code here, guys, let's see, for example, here, uppercase A. Uppercase A, it's converted to hexadecimal 41 or decimal 65, okay? 65 or 41 are the same. They are equal to each other. But 41 is in hexadecimal, 65 in decimal. They are the same, okay? So you can see here all the letters, all the characters. So this is for uppercase, as you see here, and this is for lowercase. So what this means? Very simple. It means every time you type, when you type here, letter A, so the keyboard is gonna send 41, number 41 to the microcontroller. Is that okay? Because again, we need to do conversion because microcontroller can only understand binary numbers, okay? Same thing, if you want to display something on the LCD here, you see the LCD, or you want to display something on the monitor here, okay? So I'm gonna teach you later in this course. If you want to display something on the LCD, for example, I want to display letter A, for example, okay? So you have to write the ASCII of A, the ASCII of A. So if you send 41 to the LCD, you can see letter A. Is that okay, guys? So again, we have a table. This table is called ASCII code. This table has all the characters, okay, all the letters we have. Even if you see here, even numbers. So numbers here, okay, every number has ASCII code. So if I want to display number 0, I should not send 0. I should write 30, because 30 is the ASCII of 0. Okay, so if you want to display 0 here, I have to write 30 here. Yes.
So, for example, if you want to say hi with exclamation point, what that look like?
Hi is two characters, right? So if I want to display here hi, so hi is HI. Okay, so H here 48. So number one, I have to send 48 to the LCD. Once I send 48, you will see letter H. Okay, then you have to send I. If you want to make it a lowercase, so you have to send 65. If you want to display it 49, so it has to be character by character. You have to send one by one. Is that okay? Okay. So, and also you can see here, guys, the uppercase or lowercase, they have the same difference. So if you see here, guys, this one is 41 and this one is 61. Okay, so always, as you see here, if you want to convert from uppercase to lowercase, you have to add 20 hexadecimal. And if you want to convert from lowercase to uppercase, you have to subtract 20. You can see, right? So you can see here, for example, this is Q 71. Q here is 51. Okay. So you have to add 22 anyway. So as you will see later in this course, if you have a string, something like that, and you should have done something like that in C language before. If you have something like that in C language, okay, you define a string this way. You define a message. You define a string this way. So how this string is going to be stored in memory? How it is stored in memory? Okay. So the way, as I told you guys, so I want to store this one in the memory. Okay. So how it is stored in memory? As I told you, we have to store the ASCII of each character. So the way it has to be done, this is A. So this is the ASCII of A, the ASCII of R, the ASCII of M. M is here. Space has an ASCII. You have to put the ASCII of space and so on. So you have it is stored this way in memory. Okay. So I'm gonna explain more about memory, but for as you see here in the memory, we have locations. We call it addresses. I'm gonna explain it in details. So every location in the memory can store only 1 byte, as you see here. And every location has a number, location number, we call it address, right? So the beginning address is going to be the same name like this one. So str is going to be resolved by the beginning address. So if this one is stored at location, for example, number 7,000, so str is going to be 7,000, okay? So anyway, so wherever it is stored, str is the name of the array is going to give you the first location. Next location you add one, because as I told you, as you see here, sorry, give me just 1 second. See what happened. Okay, so okay, guys. So what I'm saying is that it is stored in locations in memory. I'm going to give you more details later about memory. But again, the main idea here, if you have a message like this one or you have a string, we have to store it in ASCII, as you see here. Even a space should have an ASCII, as you see here. And they stored in locations in memory, as I'm going to explain later in details. Also, we add a special character at the end. If you remember from C language, we add a special character which is 00. So 00 here, this one is not here, right? But we put 00 just to indicate this is the end of the string. Okay, we call it a delimiter, just to know this is the end. So if I start from here, I can read all the characters until I find this one. So this is a delimiter, just to tell me this is the end of the string. Okay, guys. You can see here, these are the ASCII of the uppercase letters. This is the ASCII of lowercase letters. You can see very easy. If I want to convert between cases, from here to here, you have to add 20. From here to here, you have to subtract 20. Any question, guys? Okay. Right. So now in the second part here, I'm going to talk about computer hardware organization. Okay. So here, this is the architecture of any computer system. This is the architecture of any computer system. And I want to tell you, what do you mean by computer system? Computer system, it can be your PC, it can be your iPad, it can be your tablet, it can be your smartphone, because all of these are computer systems. In this course, we are interested in microcontrollers. So this chip, as you will learn in this course, this chip also is a microcontroller. It's a computer system, right? So it has this architecture. So any computer system, computer system doesn't only mean your PC or your laptop. No, any system that has this architecture is this is a computer system. It's a computer, right? As you will see in this course. Okay. Anyway, so any computer system, as you see here, should have a processor. We call it CPU or processor, whatever you call it. Also, it has memory. It has input devices and output devices. Also, it has what we call buses. And we have 3 types of buses: address bus, data bus, control bus. Okay. So now I'm gonna explain each piece in details, one by one. I'm gonna explain them in details. Okay. So let's start with the first one: input device. That's the easy part. Input device. What it means? Input device, you can tell from the English name. this device should send the data to the microcontroller. So any device that sends the data to the microcontroller, we're gonna call it input device. So this input device, it can be a sensor. Sensor is reading something and is sending data to the microcontroller. It can be the keypad, this keypad here. It can be a switches. It can be push button. Okay, any device that sent microcontroller is gonna read from this device. So this is input device. Okay. If the microcontroller is gonna write data, look at the arrows, very important direction here. So if the microcontroller is gonna read data to this device, we call it output device. So the output device here, it can be LCD. So I'm gonna write to the LCD. It's gonna be 7-segment LEDs, for example. We have a buzzer here. Buzzer. This buzzer can make some kind of noise. Some kind of noise here. Okay, like alarm or something like that. So any device that microcontroller is gonna send data to it, so it's called output device. Okay. Also, we have what we call memory, and look at the arrow here. We can write to the memory, we can read from the memory. Okay. So now, tell us what do you mean by common bus? What do you mean by bus here? Okay. Look at the idea. The idea is that we have system, this system. Okay. How can we connect everything together? How can we make connection? So here, this is a very simple picture, right? Because here it has only one input, one block for input unit. In reality, you may have many input devices. You may have many output devices. So how can we connect everything together? So that what usually we use in computer system, we use the idea of bus. So what is bus? It's a common bus. It's a common bus. Okay. So this bus is just wires or connectors, conductors, wires. So what's going to happen is that if input device want to send some data to the processor, it has to write the data to the bus here. So here, so it has to write, the input device has to write to the bus, and then microcontroller can get it from the bus. The microcontroller can read it from the bus. Okay. So this is how can we make the connection easy. So instead of connecting every device to the microcontroller, no, we don't do that. What happens is that we have one bus. Okay. All the devices are connected to this bus, all of them. Okay. So if one device when I send data to the processor, so this device is gonna write on the bus. That's why we call it a common or shared bus. And then the processor is gonna read it from the bus. Okay. This is what usually we do. Okay. For sure, by common sense, two devices are not allowed to write at the same time. For sure. Okay. So there should be some kind of coordination. If you want to write, so after you are done, I'm going to use the bus because it's a common bus, right? Two devices cannot use it at the same time. You have to use it first. When you are done, I'm going to use it. So only one can use it at a time. That's true. Okay. Anyway, so we have three types of buses. I'm going to give you more details about them right now. So we have here data bus, we have address bus, and we have control bus. So I'm going to give you more details. So now I'm going to explain memory, give you more details about memory. So I'm going to explain why we need memory. So how we're going to use it in how we're going to use it here in this computer system, and how it is connected. Okay, so that's what I'm going to explain now. So here, you know, as I told you, we have a processor. The processor has to do only one thing: execute programs. That's it. So as you will see in this course, also as you will see in the lab, processor should execute programs, execute instructions. You have assembly instruction. This assembly instruction the processor can execute them by the hardware. The hardware is going to execute this instruction. That's all what processor is going to do. Okay, but the processor alone is not enough to create a system, right? So I need memory. I'm going to tell you why. I need input devices. I don't need to tell you why I need input device, because if I want to read data from the user, so I need input device. Also, I don't need to tell you why in the system I need output device, because if I do some calculation, I want to display the result. So there should be some way to display the result to the user. Okay. So so here, when I explained the buses, I told you we have address bus. I'm going to tell you what exactly, give you more details about it. Data bus, control bus. Again, the word bus, it means a common. It's a common bus or shared between all devices. Okay, so it's a set of conductors or wires that carry address signal. Okay, so this one carries address signal, but this one carries data for data. This one for control signal. Is that okay? So we have three different buses based on what they carry. Do they carry control or data or address? As I'm going to give you more details. Now, let's start to, now I'm going to talk about memory. Why? I'm going to give you more details. Why we need the memory, what types of memory we have, how can we read memory, how can we write to the memory, and so on. Okay. So I can represent memory something like this block diagram. I can use this block diagram to represent the memory. So memory, as you see here, guys, a memory is arranged as a series, or it's a group of location. It has different location. Every location can store 1 byte, as you see here. Every location can store only 1 byte. Okay. Also, every location has a number, a unique number, and this number we call it address. So you can imagine memory. Again, memory is a chip. Okay, it's a semiconductor chip. It's a logic circuit. Okay. Anyway, so this memory it has locations. It has locations. Every location can store data, which is only 1 byte in every location. Every location has a number, unique number. Okay, and this number we call it address. So why we need the number? Very simple, because if you want to read any location, you have to tell me which location you want to read. If you want to write to any location, you have to tell me which location you want to write to. Okay, that's what we call address. Is that okay? So as you will see later, if assuming, for example, if we have 16 bit, if the addresses are 16 bit, okay. So how many maximum location I can have in the memory? 2 to the power 16, as I told you before. So maximum I can have 2 to the power 16 if the addresses are 16. But if the size of the address here, okay, if the size of the address is 32. So how many total location potentially we can have? Maybe less, but a total. So the total location, I can have 2 to the power of 32 locations, right? Which start from 0, 0, 0, 32 zeros until 32 ones. This is the whole space, okay? So if you are going to use the whole space, so what is the maximum memory I can use? It can be 2 to the power 32, which is 4 gigabyte, as I'm going to explain it, okay? Okay, guys, any questions so far? So now you should, that's what you are going to see in the coming lab. Okay, in the coming lab, you will see the memory. The memory is locations. You will see every location is storing only 1 byte. You will see every location has an address. Okay. More importantly now, so why we need memory here in the system? So why this system should have a memory? Very simple. Very simple. As you will see later, guys, in this course, as I'm going to explain in details, after you write your programming assembly, it has to be converted to what we call machine code. Okay. So what do you mean by machine code? I mean, every instruction you are writing in English words, add, subtract, multiply, whatever, assembly is English words, right? But every instruction has to be converted to machine code. What do you mean by machine code? I mean ones and zeros. That's it. So every instruction has a bunch of ones and zeros, okay? And then these ones and zeros, if you put it on the hardware is going to do this operation. You understand what I'm saying? As I'm going to explain details anyway for now, but you should for now understand any program has a number of instructions. Every instruction has a code, zeros and ones. Is that okay? So the question is, okay, This is a computer system. Any computer system should execute a program. That's it, right? Computer systems are used to execute programs, right? So there should be a program. So where this program is stored, this is a question, where it is stored. Is there a space here inside the processor to store it? The answer is no. So that's why we need a memory. So I need a memory to store the program in this memory. Make sense? Okay, so number one, the memory, we need memory in the system so that it can store my program, because my program is going to be just a bunch of ones and zeros. Okay, and then as I'm going to explain later in details, what's going to happen is that now microprocessor is going to read instruction by instruction from memory. You get what I'm saying? So all the program is stored in memory, right? What's going to happen? Microprocessor is going to read, give me one instruction, execute it. Give me one instruction, bunch of ones and zeros. Put it on the hardware is going to do this operation, right? Once I'm done with this instruction, I need to ask the memory to give me another instruction to execute it, and so on. You got what I'm saying? So I need a place to store the program in binary, and then all the time microprocessor is going to ask the memory, please give me an instruction. I'm going to get one instruction, execute it. I'm done with this instruction, so I have to move to next instruction. That's what we do for any programming, for any program. Then I'm going to ask the memory, give me the second one, okay, and so on. Okay? That's why in the memory I have to store number one, code, my code or programming machine code, and that's what you are going to see in the lab. Okay, you will see the code in assembly. You will see how this code is going to be written in memory in ones and zeros. Okay, and then you will see how microprocessor is going to read one by one, execute one by one. Is that okay? Also, I need memory to store data. In your program, you have arrays, you have variables. Okay, so where I have to store these variables and arrays, also in the memory. So now I need a memory so that I can store the data for any program. I have data. Also, I have instructions. So both of them are stored in memory. That's why you need memory. Okay. And so now what I'm explaining here, guys. Here I want to show you how it is connected. So as I told you, the memory is like a chip. Okay. How it is connected to the microcontroller. Okay, it's connected. As you see here, we have address bus. Okay, but I just here only this is a complete system, so we have also input-output devices. But I just want to show you the only two devices, processor and memory. Okay, but in reality, all of them are here. Okay, so as you see here, yeah. So as you see here, guys. So here, processor, it has address. Okay, whatever in bits. Why you are calling it in bits? Because this can be different from one microcontroller to another. But some microcontrollers, they tell you this 16 bits, or it can be 32, it can be more. So it's different from one system to another. Okay. So this address is gonna select a location to read or write from this location. Is that okay? So addresses, you have to select it. I cannot tell the memory, give me a byte. Doesn't make sense. You have to tell me the memory has too many bytes. You have to tell me which location you want to read or write. Okay. All the time, microcontroller is reading all the time. Reading means the data is going to move from memory to the processor, or writing. Writing means the data is moving from the processor to the allocation here. In both cases, either you are reading or writing, you have to tell me which location. Yeah, right? You need read or write, and so on. Also, you have data here. This is the data you want to read. Okay, so look here. This one is bidirection, because if you want to read, it's going to be this way. Sorry, if you want to write, it's going to be this way. If you want to read, it's going to be this way. Okay. Okay. Also, is that everything? So here you have some wire here, because again, this you can think about it like chips. These are chips, so these are wires. That's true. Okay, but it's a bus anyway. So this is a bus. So yeah, so we have here wire to transfer the data. We call it the data bus. We have some wire here to look at the direction. So always address, it's unidirection, always this way. Okay, but data can be bidirectional. Okay, so is that everything? No, that's not everything. Okay, we need also control bus. Okay, so for example, here for the control bus, I need two things. this one should give instruction to the memory to start reading, or this one should give to start writing. Okay, so only one of them is one at a time. So for example, this one is 1, so this one has to be 0. Okay, so if you want to start reading, so this one has to be 1 and this one has to be 0. If you want to start writing, so this one has to be 1 and this one has to be 0. And the hardware of the memory is designed so that once this one is 1, the hardware is gonna read or write. Okay, so now I just want to give you idea how, and this happens all the time, by the way. So all the time processor is reading and write every time a microprocessor has to read one instruction, execute it, okay, and then read another one, execute it. All the time you have variables. These variables are locations in the memory. You want to read the variable, you want to write to the variable. So all the time microprocessor is reading, writing, and that's all what the memory is doing, just reading or writing, okay. So now I'm gonna give you examples just to understand how it works. Okay, just quickly. For example, I wanna read the location. For example, 300. I wanna read whatever is stored in location 300. So how this can be done by the hardware? Okay, again, it has to be done in steps. Okay, there are some steps it has to be done, but that doesn't mean when I come to assembly, you have to write instruction for each step. No, it's just that you can just write one instruction, but to execute this instruction is going to be done in steps. So number 1, if I want to read the location 300, so the processor number 1 has to write here 300. Okay, that's it. So once you write 300, the memory is gonna read the content of 300, put it here. No, I have to give the command. I have to order the memory to do that. How can you do that? I have to put here 1, you have to put here 0. So this is step number 1, okay? Once I put the address, now I'm gonna ask the memory to start reading. Okay, step number 2. After that, the memory is gonna put the data here. Whatever is stored in this location is gonna copy it here. Copy means the value is not gonna change, okay? For example, in this location, if we are storing 2A, for example, so this one, what you are gonna write here 2A, right? And then still the location has 2A because reading does not change whatever is it. Then the processor is gonna take 2A. This is how can you read the location, okay? And actually, exactly what you did in C language. In C language, when you define variable, integer I, integer J, when you define a variable like this one, I'm not sure if they told you or not in C language, but every time you define a variable, there is a physical location in the memory is going to be stored for I. So every time, but the exact location is hidden from you because this is high-level programming language. So for example, if I assign location number 300, if I assign 300 for I, for your variable I. So every time you write to I, I'm going to write to this location. Every time I want to read from I, I'm gonna read from this location. So every time you define a variable or array in C language, this should be a physical location in the memory. But you may be, because this high-level programming language, maybe I don't need to know all what I need. Just I want to write in this variable. I want to read from this variable, but it may not be important for me to know. Although you can, if you know the exact where it is exactly stored in memory. But anyway, so this is how. So reading has to be done in 3 steps, as I said right now. I want to give you another example for writing. If you want to write, for example, in location number 7000, for example, I want to store the value FF. How this can be done? Okay, number 1, the processor has to put here 7000. Okay, the address here. Number 2, the processor has to put here the value FF. Make sense? Done? Is that done? Memory, it's gonna write by itself? No, I have to give the command. Once the address is ready, once the data is ready, I have to give the order of the command to the memory to start writing. Okay, so here I'm gonna put here 1, I'm gonna put here 0. Once I do that, the memory is gonna take this value, is gonna store it in location 7000. Is that okay, guys? So all the time This is how it works, read, writing, and so on. So now you should understand, guys, any computer system we should have memory. You should understand that. This memory is going to be used to store instruction. Also, it is used to store data, and also it is used for stack. But later I'm going to explain what is a stack and we need it, why we need it, and so on. Okay, so forget it for now. But this is used for now for data and instructions. Also, in case of low-level programming language, you have to make sure there is no overlapping between them. Otherwise, your program may crash. You get what I'm saying? What do you mean by overlap? You have the memory, right? So you have to make sure they are in separate locations. This is, you need to do some kind of memory management. So this area is going to be for instructions. This area has to be for data. You get what I'm saying? So you have to make sure of that. If there is overlap, your program will crash, right? So if you write the instruction and data in the same locations, it may crash, right? So, you know. Here, so now, guys, you should understand why any computer system should have a memory. You should understand what I mean by addresses, what I mean by data. You should understand all the time. This is how it works for any computer system, okay? PC or any computer system. All the time, PC is reading, writing, reading, writing, all the time, reading, writing, reading, writing, okay? The other thing here, we have different types of memory. Maybe the very famous ones are, or the widely used one are SRAM, static random access memory, SRAM, okay? Also, we have flash memory, okay? So we have different types of memory, but this usually in computer system, we have these two. In the RAM is volatile, okay, volatile. You know, this means if you turn the power off, you are going to lose everything there. But in flash memory, it's non-volatile, right? So that means if you turn the power off, it's going to keep the information there. So why, as you will see later in this course, why we need these two kinds of memory, why, and how we're going to use it? Very simple. So what we're going to do, guys, here in the flash memory, I'm going to write the program. So the program is going to be written in the flash memory, okay? And your variables, your arrays are going to be here. Your variables, your arrays are going to be here. Why you made this way? You made this way. I'm going to tell you why. So that, because this one is non-volatile, the flash memory. That means if your device is losing power, if you lose power, still you have your program. It's going to work. You get what I'm saying? Because the program itself is stored in non-volatile memory. So usually you put the program here and your data here in the RAM. Why? Because the RAM is much faster to read or write, is much faster than the flash memory. That's why we use this one, use RAM for data, and we use this one for program. Okay, guys, any questions? Okay, so the last thing I want to teach here, guys, I told you memory has location. Every location is storing 1 byte. So in every location we store 1 byte. So okay, someone can ask me, okay, so what if my number is half a word? As I explained to you before, it can be half a word. Half a word means 16 bits, right? It can be 32 bits. 32 bits. Here, 32 means 4 bytes, right? So this is a word. So how it is stored in memory? If every location, if your number, okay, so I'm measuring something, measuring temperature, pressure, I'm measuring something, and whatever I'm measuring, I'm storing it in half a word or in a word, right? So the question is that, okay, how I can store it? How this number is going to be stored in memory? You got what I'm saying? Given that the memory can only store in every location, store only 1 byte. Okay, very simple. So what you have to do, you have to store it in consecutive locations. Okay, so for example, if my number, for example, is 3A, for example, F2, this is my number is half a word. So this one is going to be stored in 2 locations in memory, not only 1 location. Is going to take 2 locations, and so on. Is that okay? And that's what you are going to see. So you are going to see in this course, in labs, when you define a variable, you will see if this variable is going to be stored in more than 1 location, because every location can store only 1 byte. Okay. Any questions? Okay. Now I'm going to move to the processor. Okay, I told you any computer system should have a processor, or we call it a microprocessor or CPU, whatever you want to call it. As shown here, guys, the processor has three main things here. It has control unit, it has arithmetic logic unit, ALU. Also, it should have registers. So any processor should have these 3 things: control unit, arithmetic logic unit, and registers. So now I'm going to give you more details about them. Okay. Let's start with arithmetic logic unit. Keep in mind, guys, everything I'm explaining here, hardware, okay, devices. So register is a hardware. Arithmetic logic unit is a hardware. Okay. Control unit is a hardware. Okay. So now I'm going to start with arithmetic logic unit. The arithmetic logic unit, guys, you can tell from the English name, this unit is responsible or this should perform the arithmetic and logic operation. So if I want to add 2 numbers, this unit is going to do addition. If you want to multiply, it's going to do multiplication, and so on. Okay. So here I want to give you here I'm giving you example for a very simple toy ALU, very simple ALU. Just I want you to understand the idea. Okay. So this ALU, it can do 4 operations. It can do 4 instructions. I'm assuming I have a very small computer just to get the idea, to understand how everything is working. So I'm assuming this computer, it has 4 instructions. So this computer can do addition, add instruction. It has subtraction. It can do AND, logic AND. It can also do logic OR. Is that okay? So now I'm going to explain to you, and every instruction has a machine code, something like a machine code. Okay, this code, for example, 00, 10 or 01 or 11. Okay, so every instruction has a code. Okay, so the interesting part here, guys, this you will see right now how the hardware is designed, so that when I put here 00, this one on, this one off, this one on, this one off, so that at the end I'm gonna do addition. If I put here 10, the hardware is gonna do subtraction. Okay, and so on. Just I want you to understand. By the way, this chapter it's a big topic. This can be a course by itself, computer architecture is a course. But I just want to teach the minimum information we need for this course. Okay. So after I explain this example, you should understand, guys, very important thing. As I told you guys, the big difference, as I'm going to explain, the big difference between C and assembly. Assembly is machine code, but using English words, but machine code, right? So every instruction, for example, that's exactly what happens. In assembly, I'm going to use the word add, okay? But the machine code for add is 00. So you should have like a table, as I'm going to explain right now. For every English word here, it has a corresponding machine code, right? I'm going to explain now how this one works, but what I want you to learn here, I just want to give you some idea about how instruction can be executed by the hardware. That's very important, okay? Because this is what assembly. Every instruction with an assembly has a hardware to support it. You execute it by the hardware. This is not the case in C language, as I'm going to explain, okay? So you will see right now how when I put here on the hardware, I put 00, I design the circuit so that it can do addition, can do subtraction, and so on, okay? But before I move forward to show you how it works, I just want to make a quick revision about multiplexer. So because we are using 2 multiplexers here, 2 multiplexer. How multiplexer works, as you know before, multiplexer is a logic circuit. It's a logic circuit. This logic circuit, it has a selector, and it has input, and it has output, as you see here. Okay? So if you input 00, If you input 0, 0, so that means the output should equal to input 0. So here, the output is like the output is equal to this one. Okay, it's like a switch, it's exactly like a switch. So if I put here 0, 0, so if I put here, guys, 0, 0, so you connect the output here to I0. If you put here number 1, so the output here, the output will come from here, and so on. So you can control the output. You can connect the output here to any one of these inputs based on the value here, logic, hardware. So this is hardware circuit and using one sensor. Anyway, so let's see. I want to show here, guys, and this is the important thing I want you to understand. How, when I put 0, 0 here, how this circuit is designed so that at the end you are going to get addition, right? So let's see how it works. Again, this is not a real computer, but I just want you to get the idea or fully understand, because that's exactly what happens in reality. The hardware is designed so that when you put the machine code in the hardware, right? So the hardware will do this operation, okay? The assembly one. Okay, so let's see. For example, if you have here, I'm gonna put 0, 0. So here I have logic circuit, hardware, I call it comparator. So this one is gonna compare the input here to 0, 1. If they are not equal, so this one output 0. If they are equal, this one is gonna output 1. Okay. So in this case, because this is 0, 0, and this one is 0, 1, so we're gonna get 0 here. And because this is a multiplexer, it has two inputs, input 0 or input 1. Okay. And now because this one is 0, so the output is gonna connect it to input 0. So here CN is going to be connected here, okay? And also because this one is 0, so this multiplexer has two inputs, either number B, this A and B, these are the two numbers. I'm going to do the operation on these two numbers, okay? So A and B. So here, this one should select, this multiplexer, you can select either B. If you select input 0, you are going to select B. But if you select 1, so it's going to be B prime, because this inverter. So using this multiplexer here, let's select either B or B prime. B prime means the one's complement to B, the one's complement to, the one's complement to B. Is that okay? So anyway, this is because this is 0. So B is gonna come here to the hardware other, and also A is always here. Okay. So now this other is gonna add B plus A plus 1 bit, we call it CN, carry N, CN, okay? And then the output, this other has output here, the summation here, okay? The summation, and because the input here is 0, 0, so the output of this one should come from here, from the sum, okay, is that okay? So that's why I'm gonna get A plus B plus carry, okay? So A is in-bit number, B is in-bit number, and this other is going to add in-bit number to in-bit number plus 1 bit. We call it carry. Okay, forget it for now. Why sometimes I need to add the carry? Okay, I'm going to explain it later because there is a reason for that. But for now, see it like I'm going to add A plus B. Is that okay? Now, again, if you don't understand it, do your best to understand it. But if you don't understand, again, it's okay. What I want to explain here, guys, I just want to convince you how computers work, how computers work, how the hardware is designed, so that once you have a machine code, put it on the hardware will do these operations. That's how it is, okay? So now I'm going to show you how when I put 0, 1, I'm going to do subtraction, okay? So let's look at this one. Here, if you put 0, 1, this one is 0, 1, and this one is 0, 1. So this is a comparator. So here I'm going to get 1. So the output of this one is going to come here. The output here is 1. I made it this way. I put here 1 for a reason, right? So I designed it for a reason, okay? So here I put 1. So that 1 is going to come in. Number 1 is going to come here, okay? And then here, because this one is 1, I'm going to get the input from here, which is B prime, B prime. So if you look at the input of the other has A plus B prime plus 1, A plus B prime plus 1, B prime plus 1, b prime plus 1. What is this? This is negative b because of the 2's complement, right? The 2's complement is the 1's complement plus 1. You get what I'm saying? Okay, so that's why b prime plus 1, this means b prime plus 1 is negative b. That's okay. That is why the people like the 2's complement, because as you see in this example, using the same circuit, the same other, I can do addition and subtraction, the same hardware. That's why the people like that. So it's not the case for other systems. I told you to represent the negative numbers, we have different systems, okay? But most of the processors are using the 2's complement system because of that. Okay, it's efficient on the hardware. You can see using only one hardware, I can do, because actually subtraction is addition. That's what I did. Subtraction is addition. But it's addition to the complement of the number plus number 1. That's it. You got what I'm saying? Anyway. So again, the most important thing you should learn from here, guys, this is like a very small computer. That's exactly what happens once you have this code. Okay, you put the code on the hardware is designed, okay, in such a way it's gonna do this operation. Okay? And now, same thing for sure if you wanna do AND or logic or whatever. Okay. Any questions before I move forward? Okay. Now, any processor should have what we call instruction set. Any processor should have what we call instruction set. In this instruction set, guys, it should be something like the table I have here. Okay. This is assembly instruction, like for example, ABA. This is English word for assembly instruction. So what this one is gonna do is gonna add register A plus register B, store the result in register A. Okay. And this instruction should have a machine code. This is the machine code, 1806. Is that okay? So all the instructions supported by this microcontroller should be here. That's what we call instruction set. So any company when they manufacture a processor, they should give a table like this one. This table should have instruction set. So again, what do you mean by instruction set? I mean all the instructions the microprocessor can execute for sure by the hardware. Is that okay? So you should get a table like this one for any processor. Okay. And why number 1806? Okay, this is a machine code. Okay, this is because the people who made this microcontroller decide to select this number so that when you put it in the hardware is going to do this operation. You got what I'm saying? Any questions? So you should understand, guys, every processor should have an instruction set. Every instruction is executed by the hardware. Is that okay? That's why every processor has a limited set. I cannot increase. I cannot add one instruction. I can't, because every instruction has a hardware. You got what I'm saying? So that's what we call instruction set. Also, every instruction should have instruction like this one, assembly instruction, which is English words like add, like subtract, English words, right? And every instruction here should have a machine code, corresponding machine code. Is that okay? And that's what we are gonna do in this course. That's what we are gonna see in the first lab. So in the first lab, I'm gonna give you a code written in English words in assembly, and you will see by yourself this every instruction here is going to be translated or is going to be converted to the code and stored in memory. Is that okay? Again, that is why, listen to me, that's why if you program using assembly, it's almost the same thing. If you program using machine code, it's almost the same thing. The only difference is we as humans, we hit numbers. We just like English words. That's it. Just to be more convenient for us, if I want to do addition, instead of writing 1806, I'm going to write ABA. Because just we we like English words. It's easier for us than numbers. You get what I'm saying? So, and then we're going to use a program. This program is called assembler. Assembler. Okay. This assembler should take the English words and convert them to machine code. Okay, and to store them in memory as you will see. Okay, guys, any question? So every instruction you write in assembly is going to be translated to machine code and stored in memory. That's why if you program in machine, this assembly program is very simple program, very simple. It doesn't too much. All what it has to do, just replace the English instruction you are writing with the corresponding code. That's it, very simple. Okay, guys? This is not the compiler. The compiler used before. The compiler is too complicated, as I'm gonna explain after I finish this part. I want you to understand it. Okay, compiler is too complicated because it's high level, but assembly is low level, right? So as assembly is very simple program. It's gonna convert every instruction is gonna be converted to numbers. That's a very simple program, right? Compiler is too complicated. Okay? And yeah, I can explain it here, guys. For example, that's exactly what we are gonna do. This is the assembly, right? So what happens here, guys, in assembly, you are gonna write English word, something like that. English word, something like that. Move SR10 and so on. So for sure, I'm gonna explain later what it means. Okay, so this is assembly. Every instruction here is gonna be converted to machine code, right? It's stored in memory, right? So maybe this depends on the instruction. If this instruction takes 2 bytes, so are going to be only 2 bytes. If it takes 4 bytes, it's going to be stored in 4 bytes and so on. So it's going to be converted. So every instruction here is going to be converted to just similar to what I said here. So here, if this instruction is going to be converted to this one, every instruction in assembly is going to be converted to one instruction in machine code. That's it, and stored in memory. Who's going to do that? Assembler. And again, this is just a very simple program. However, compiler is a different story. Compiler, guys, this is what you have used before. Again, let's agree, processor can only understand this one. Microprocessor can only understand this one. So what happens is that if you write your program in high-level programming language like C language or like Java or whatever, so you need a compiler. This compiler has to convert this one to assembly. And then after that, it's easy to convert the assembly to the machine code. Is that okay? And in this conversion from C language to assembly, maybe one instruction here is gonna be converted to 10, 20, 30 instruction in assembly. You got what I'm saying? So unusually, so here, this is not straightforward. This is too complicated. It's not easy. You got what I'm saying? Because this one is too high level. You are very far from the hardware. So I need a smart compiler in order to get this one and try to make assembly, the equivalent assembly. So that these assemblies can do the same thing like what you did here. Again, what is the biggest difference between assembly? You should understand. What is the difference between assembly instruction, machine code, and high-level programming instruction? What is the difference between them? Again, programming using assembly to me it's identical to programming using machine code, but just instead of using numbers, I'm gonna use English words. That's it. Okay. So every instruction you write in assembly is gonna be translated to one instruction in the machine code, right? So programming using assembly is similar to programming using, it's actually machine code, right? Okay. However, programming using high-level programming language, this is high level. Processor doesn't understand any of this instruction. Processor doesn't understand what is for. It doesn't understand what is while. It doesn't understand all of that, right? So that's why you need a compiler to convert this one to assembly. And in this conversion, maybe one instruction here is going to be translated to more than one instruction here. And it needs some kind of intelligence, okay? And usually the people are complaining, usually this conversion is not efficient, okay? That is why, as I told you, as I said last time, that is why if you want to make a fast program, very fast program, If you want to make efficient program, usually the people do it in assembly, not in C. Why? If I want to do something like in C, because the compiler is not smart enough, okay? So it's going to take this amount of assembly, for example, okay? So this amount of assembly has to be stored in memory. So it's going to take long time, for sure, relatively long time. Also, it's going to take more space in the memory. However, if you do the same task using assembly, it's going to be shorter, right? That's why if your program is very critical about time sensitive, very critical, the people do it in assembly. Any question, guys? We still have 1 minute, okay? So any question? Yeah, 15 is 15, okay? It's 14 now. Okay. Again, you should you should fully understand what is the difference between assembly instruction, machine code, and between high-level programming instruction. You should understand what is the difference between assembler and compiler. You should be convinced. You should understand this instruction executed by the hardware. You should understand assembler is a very trivial, very simple program. Instead of writing, actually we have a table like this one, instruction set. Instead of writing 1806, I'm gonna just write EBX because we like English words more than okay. But this is not the case for compilers. Okay, this is not the case. That's why if you need to like you program very fast program, time is too critical. So usually the people do it in assembly instead of C language. Okay, guys, because usually compilers are not very smart, okay, like us for sure, like humans. So something can be done in this code. Maybe the compiler is going to do it in more because it's not easy. It's not easy to convert it from high level to assembly. Okay. Any question, guys? So again, we're going to meet tomorrow 4:30, right? 4:30, like 1 hour and a half or 2 hours, and that's it. Okay? Because I need to finish to start lab 1. I need to finish chapter 1. Okay.